The closest supernova remnant, Cassiopeia A, is a very well-studied object that came back to the news due to the recent observations made by the James Webb Space Telescope, giving us a new view of the expanding shell of material slamming into the dust that was formed by the material that the progenitor star shed before it exploded. Cassiopeia A, as its name says, is in the constellation of Cassiopeia, and it is just about 11,000 light years away from Earth. Astronomers estimate that the star giving rise to Cassiopeia A had at birth about 16 times the mass of the Sun, but by the end of its life, it had already shed 2/3 of its mass, leaving it with only close to 5 times the mass of the Sun before it exploded. Cassiopeia A is 10 light years in diameter, and astronomers estimate was produced by the explosion that happened about 340 years ago. Because it is at an early stage of evolution, there is a great deal of information that can be obtained in many types of light, going from X-rays to radio waves. NASA Chandra X-ray Space Telescope has been observing Cassiopeia A since it was launched in 1999, revealing information about its central neutron star that was left after the explosion, which seems to be rapidly cooling. It also gives us details of the explosion and specifics of how the exploding debris ejected into space. Chandra images provide the location of the different elements that were synthesized in the original stars and that now are in the remains of the explosion. In Chandra image, we see silicon in red, sulfur in yellow, calcium in green, and iron in purple. The high energy X-ray emission is in blue, which also includes the outer layer of the expanding blast wave. From these observations, astronomers derive that Cassiopeia A has dispersed about 10,000 Earth masses worth of sulfur and about 20,000 Earth masses of silicon. The iron in Cassiopeia A has a mass of about 70,000 times the mass of the Earth, while the amount of oxygen is equivalent to about 3 times the mass of the Sun. These and other elements also observed by Chandra and other telescopes make up all the elements needed by the DNA, the molecule that carries genetic information about the life in our planet. In this representation of the periodic table of elements, we can see how the different elements we know were produced in the cosmos and how those contribute to the life as we know it. Other observations taken in the visible and near ultraviolet light with the advanced camera for surveys on board of the Hubble Space Telescope show something different. In this case, we see a broken ring of bright filamentary and clumpy stellar ejecta. The swirls in here are produced by the glow of the debris heated by the passage of the shock wave from the supernova blast. Just as before, the various colors indicate different chemical composition. In the image here, the bright green filaments are rich in oxygen, the red and purple are sulfur, and the blue is mostly hydrogen and nitrogen. We have a different view in the infrared light obtained with the mid-infrared instrument MIRI and the near-infrared instrument NIRCam on board of the Webb telescope. The images here reveal new and unexpected features within the inner shell of the supernova remnant. The tiny clumps represented in bright pink and orange in the NIRCam image make up the inner shell and include sulfur, oxygen, argon, and neon. These appear embedded in smoke-like clouds, which are actually a mixture of dust and molecules. Some filaments of debris are too tiny to be resolved by Webb, meaning that these are less than 10 times the distance between the Earth and Sun. The MIRI observations reveal other aspects of the composition and behavior of the supernova remnant. Here we see a deep orange and red cloud in the outer skirts of the Cassiopeia A main inner shell, giving us insight of how the dust in the circumstellar material is being slammed into by the shock wave produced by the supernova explosion. In the mirror image, we also see in white color light from synchrotron radiation, which is commonly observed in these events and which which emits light across the electromagnetic spectrum, including the near infrared and radio. Also, in this image, we see a bright green loop off right to the center, which is still puzzling the research team that obtained these images because it doesn't appear in the NIRCam images, which prove the dust emitting in the near infrared. Other features in this image caught the attention of the astronomers making this image. At the bottom right corner of the image taken with NIRCam, there is a noticeable feature that the research team called the baby Cassiopeia A. This is what astronomers call a light echo located about 170 light years behind the supernova and produced by the light of the actual explosion reaching and warming up the distant dust. These and other light echoes were observed before by Spitzer, the infrared telescope that had much less resolution than Webb. The radio images taken with the Very Large Array Telescope in New Mexico might look less striking, but these provide a great deal of important information about the history of the star and surrounding material before the explosion. Combining the information from all these powerful telescopes will help astronomers learn more about the history that gave rise to Cassiopeia A, how these powerful events support theories of the evolution of the universe, and how stars give rise to life on Earth.